Following on from last week, where we looked at Maclaurin series, we're going to have a look at the Taylor series to find the power series for ln x. Remember, ln x was one last week we couldn't do because it didn't exist where x is equal to 0. The function didn't exist. So the Maclaurin series anyway is a special case of the Taylor series where x is equal to 0, where you're focusing on 0. So, but what the Taylor series will do is allow you to focus on a point other than 0 for that function. Okay? So, as we discussed last week, ln x doesn't exist where x is equal to 0, which means you're unable to use the Maclaurin series to determine a power series for that function. This means we'll have to use the Taylor series, which doesn't have that condition. We can focus on a different point. And we defined the Taylor series as is on there, and we saw that it expanded to a function like that along the bottom, where we got a constant term, or a term for the function, first differential times x minus a, second differential, third differential. We can carry that on like so. So what we're going to have to do is see how that would work for a function ln x. So what we're going to do, what you're going to do, is starting with, we're going to let a equal 1. So we're going to focus on a different point to 0, because we can't do that. If we could, we'd be able to use Maclaurin series. Our function is ln x. What I want you to do is go down here and find the first, second, third, fourth differential. When you get to the red line, can you see a pattern that you can automatically write in what the fifth and sixth differentials are? Here, you are determining the value of this function when a, which is 1. So I've done the first one, ln a, ln of 1 is 0. Again, followed down to here, is there a pattern that will allow you to complete those two without even calculating them? And lastly, can you write a general answer to the nth derivative of a here? Can you write it out in general form using n for the nth derivative? Alright? So, 10 minutes or so, see if you can work on that. Just an aside, to do this last bit, this general bit here, you're going to need that minus 1 to the n is plus or minus 1. It says you can use that as a sign changer. Yep, for the general solution. down here for a minute. We got minus 1, x to the minus 2. We've got to multiply that by minus 2 and take 1 off the index. Yeah? What does that equal, and how else could you write it? Now a little bit of notation we've been using. Yeah, it is 2, and we can write it as 2 factorial, x to the minus 3. Meaning this is, the answer to this is just a straight answer now, written as 2 factorial. See the point of that when we come to the general solution at the end. Right? So, this one is going to be, we've got to bring minus 3 down and multiply by 2 factorial. Yeah. Or how could we better write the minus 6? Minus 3 factorial, x to the 4. Making the result of this just 3 minus 3 factorial. So what are these answers here then? Without doing that side, what are they? Four factorial. Look at the pattern. Minus 5 factorial. Yep. Okay. So how can we get this, the number here, something factorial from n? Forget about the positive and negative sign at the moment. But n here was n equals 6 there. Yeah, n minus 1 factorial. Is that it? Yeah. So that will give us the number factorial. How can we get the correct sign change? We want a negative. We want the result of this to be minus 1 when n is even. How can we get that? Apply that to each of these ones and see if you get the right result. If we apply minus 1 to the n here, minus 1 to the 6, does that give me a positive or a negative result? As it stands. Negative. Does it? Minus 1 all raised to the power of 6. Try it on your calculator. Make up your mind. You need to put the minus 1 in brackets on your calculator. It's even. We want it to be odd. So can we not do that by saying us x to the n minus 1 to the n plus 1? Does it now work? When that's even, it's going to make n odd, making that bit equal to minus 1. When n is odd, it'll make this bit even, making that an even number. So that's the sign changer. So that's the general solution to these results. Okay, what it doesn't do is it doesn't work for that first term where the function is ln x. It only works for the differential terms. So we're going to have to add the result in for this one on its own. That's equal to 0 anyway, so it doesn't do anything in the final series as is. But we'll write it in so we know what's there. Actually, it's equal to 0, so it doesn't do anything. So that general solution doesn't work for this first term. So, placing this general rule back into the Taylor series. Okay, so there's the Taylor series. We're going to replace this bit, the nth differential of A, with our general term for the value of the nth differential of A there, minus 1 n to the power of n plus 1 times n minus 1 factorial. And all of that is over n factorial, and we multiply each of those by x minus a to the power of n. And here's that first term in there, the one that this general solution here doesn't work for, but in this case is equal to 0 anyway. Alright? You're all happy with that? See how that works. Alright? Determine what was the answer to the first? It's going to be the fact over was or one up over the 4 carry on. Okay. Like 1 and say minus 8 we've got, and we'll ignore the margin for a minute because that will say we've got 3 over they are 1 times 2 times 3 over 1, 2 times 3 times 4. Cancel. just leaving 4 on the bottom. So you could simplify that x is equivalent to leave the x minus a minus x minus a squared plus x. And so that power series should follow with focus being that's around, so it's going to focus on the point where x is equal to 1. So right, how are we doing with this then? Is that where you started? And the result of 2 times the sine of pi is? F dash is two cos x two cos pi because the cosine of pi is -1, yeah. F double dash is -2 sine x. F double dash A is equal to just the result now. Nothing. F triple dash is -2 cos x. So F triple dash at the value A is equal to 2. And we kind of see the pattern there now. None, -2, none, +2, and so on. And that carries on. And that will carry on ad infinitum. So we could write a general term. We don't really need to, because all we know is they are the coefficients of each of the terms in the power series. Slide the pen in the bin. Two. First. Two. And then 2 x minus a of 3 factorial, and then we go -2 power 5 over 5 factorial. The odd term one. Change it between positive and negative for each one. So the last one must be plus 2 minus the power of 7, the 7 factorial 2 9 factorial 5 9. Okay, if we and the fifth term, we get almost quite add and more to power series to n is infinity. They're exactly equivalent. Okay. As the same calculators. They are equivalent if you use them for sine of 2x and have a look and see what that does. Good was the coefficient of all, was the magnitude of every coefficient, just that every other term changed sign. In this case, the frequency, focus on pi over 2. Again, that'll take us to the midpoint of that sine wave. So, well, there's a reason for this. Change that to 2 cos x, 2x. So start from the cosine. 2 cos x. Cos 2x, yeah, sorry. F of x is equal to 2 cos 2x. Anyone got any ideas what they think might happen to the power series when we do that? There's